Assalamu alaikum wa rahmatullah. Welcome back, and we are continuing our discussion on chapter 5, joint distributions, and today we would like to talk about something called linear combinations of random variables. I'm just showing you the slide here. This is our target. However, I begin with my own note on that. So I would like to say the following. Linear combinations of random variables. What is the case here? What is the deal? So basically, as you will notice at the end, we have several cases that are all related. And in case one, we say the following. We have random variables that are given, random variables, x1, x2, and so on until xp. Each one of them is a random variable. X1 is a random variable, x2 also until xp is a random variable. For each one of those, we know the expected value and we know the variance. For each one, we know the expected value and we know the variance. All this is given. So for variable x1, it has an expected value of x1 and it has variance of x1, known values. For xp, expected value of xp is known and variance of xp is known, and for each one also of the others. So for x2, expected of x2, variance of x2, and so on. Okay, so in short, we have p random variables x1, x2 until xp. For each one of them, we know the expectation and we know the variance. So expected of x1, variance of x1, expected of x2, variance of x2. For xp, we know the expected of xp and the variance of xp. Now, what are we doing with these random variables? We need to define a new random variable y. So y is a new variable that we define from the other variables. How? We say that y is defined as the linear combination of the x variables. So we define y to be constant 1 times x1 plus constant 2 times x2 plus and so on until plus constant p times xp. So it's very easily seen that y is a linear combination of x1, x2 until xp, or a weighted sum. So c1, c2 until cp are constants. So if we define y to be a new variable like that, and we will see examples, you will see where we can use that. If we define y to be a new variable, the main question is, what is the expected value of y and what is the variance of y? This is the main question. Now, let's start with the expected value. It's really easy. How can we get the expected value of y? Simply, it's the expected value, and then instead of saying y, let's say c1x1. That's how we defined y. So the expectation of c1x1 plus c2x2 plus until plus cp xp. So what do? We have seen something like that before. We apply the expectation operator to each one of the terms, but we keep in mind that c1 is a constant, x1 is a variable, and so on. Cp is a constant, xp is a variable. So the expectation of these terms is equal to c1 times the expected of x1 plus c2 times the expected of x2 plus until plus cp times the expected of xp. Guess what? That's it. This is what we would like to say. If we define y to be a linear combination like this, then the expected value of y is also a linear combination of the expected values. And this is clear and easy. Now, what about the variance? We show you the variance result without proof this time. So we say the following. For variables x1, x2, x3, and so on until xp, if they are independent, this is what we begin with. If they are independent, then the variance of y, again remember, y was a linear combination of c1x1 plus c2x2 and so on. The variance of y is given as c1 square times the variance of x1 plus c2 square times the variance of x2 plus c3 square times the variance of x3 and so on until plus cp square times the variance of xp. So the last term again, cp square times the variance of xp. This would be the variance. So as you notice, the variance of y is simply a linear combination as well in the variances. However, in the constants, we have c1 square and c2 square and so on. And I think logically or intuitively, this is expected. You know, the variance itself, what's the definition of the variance of y? If you would like to prove it, it is the expected of y square minus mu y square. So we have to square this y. When we square this linear combination, you will get the squares. Okay, so this is our result again. This is our result for the variance of y in case x1 until xp are independent. So let's proceed with our slides. So this is exactly the same as we said. Basically, if x1 until xp are random variables, c1 until cp are constants, we just define a new variable y to be c1x1 plus c2x2 plus until plus cp xp. Okay? So, in other words, y is just a linear combination of the x1, x2 until xp variables. What can we say then? What we can say is that the expected value of y is equal to the linear combination c1 expected of x1 plus c2 expected of x2 plus and so on plus cp expected of xp, as we have mentioned here. So it's exactly the same. Now what about the variance? Let me start with the second line. If they are independent, if our variables x1 to x2, sorry, x1, x2 until xp are independent, and the variance of y is c1 squared times the variance of x1 plus c2 squared times the variance of x2 plus c3 squared times the variance of x3 plus and so on until cp squared times the variance of xp. So this is the result that we talked about here. That's how we can calculate the variance of y. Now what if the variables x1, x2 until xp are dependent? What if they are not independent? How can we calculate the variance of this y? We start with the same thing. C1 squared variance of x1 plus C2 squared variance of x2 plus and so on until CP squared variance of xp. But in addition to this, we add some terms that contain the covariance. Now, let me connect to our previous lectures. We have seen last time that if variables x1 and x2, for example, are independent, then the covariance is equal to 0. And this justifies. So if they are independent, we don't have these terms. If they're independent, we just have the first p terms, c1 square, c2 square, and cp square. Each one is multiplied by the variance. Okay, but if x1, x2 until xp are dependent, if they are not independent, then in addition to the first p terms to calculate the variance, we are adding also terms that have the covariance. Now let's try to understand those terms. They're easy, by the way. They may look complicated, but they're easy. What we're doing is that we are adding all pairwise covariances, pairwise covariances. So we are adding covariance of x1 and x2 plus covariance of x1 and x3 plus covariance of x1 and x4 plus covariance of x2, x3, x2, x4, and so on. But each term is multiplied by 2 simply because we are not repeating. So if we say between x1 and x2, we don't have to include x2 and x1 because it's exactly the same. That's why we have 2. So basically, we are adding the covariances between all the pairs. So we have a double summation for I and j so that I is less than j. Let me make it clear by mentioning an example. If we have only 3 terms, so imagine that we have 3 random variables, x1, x2, and x3. And we define y to be c1, x1, plus c2, x2, plus c3, x3. So we have only 3 terms in our linear combination. The question is, how do we calculate the variance of y, assuming that these variables, x1, x2, and x3, are dependent actually? They're not independent. So the variance, according to what we just said, the variance of y is equal to c1 square variance of x1 plus c2 square variance of x2 plus c3 square variance of x3, and then plus 2 times. Let's open a big bracket. 2 times, let's open a big bracket. Inside we have c1, c2 covariance of x1, x2 plus c1, c3 covariance of x1, x3 plus C2, C3 covariance of X2, X3, and that's it. That's it. These are the only pairwise terms. So we need to add the covariance between every 2. We need to add the covariance between every 2. Since we have 3 of them, so we have the covariance between 1 and 2, between 1 and 3, and between 2 and 3. And we are not repeating simply because the covariance between 1 and 2 is the same as the covariance between 2 and 1. That's why we don't repeat. So we just stick to 1, 2, 1, 3, and 2, 3, and we have the term 2 outside. In any case, for our problems, we focus more on the independence. So we can continue with our discussion, and we have an example actually in which we apply what we just learned. So the best way to explain the example is on my own notes here. So in this example, We have a semiconductor material. You know that a semiconductor has three types of materials put next to each other. So we have an N-type material and we have a P-type material, another N-type material. In any case, all these details are not needed for this course. So the only thing that we say is that to build this semiconductor, we have three layers, 1, 2, 3, and each layer has length actually. So X1 is the length of, or the thickness of layer 1. X2 is the thickness of layer 2. X3 is the thickness of layer 3. In any case, it is given to us that X1, X2, and X3, each one of them is a random variable that are all independent. You know, we really wanted X1, X2, and X3 to have specific values, but these are really small thicknesses. So in nanometers, they're very small thicknesses. So in the manufacturing process, we can get some errors. That's why each one of them ends up being a random variable. So X1, X2, and X3 are three random variables that are independent. In addition to this, the problem, if you read it later, the problem tells us also that the variance of X1 is equal to 25 nanometers squared, and the variance of X2 is equal to 40, and the variance of X3 is equal to 30 nanometers squared. Now, what is the question here? The question is find the variance of the total thickness. If we know the variance of X1 and the variance of X2 and the variance of X3 separately, the question is what is the variance of the total thickness? Now, how can we express the total thickness? Obviously, it's simply X1 plus X2 plus X3. So we have to add the three thicknesses to get the total thickness, and let's just call it Y. So let Y be the total thickness, which is X1 plus X2 plus X3. And the question is, find the variance of Y. So how can we find the variance of Y? We notice Y is just a linear combination. So it falls under the case that we have just studied. Y is a linear combination. However, all the constants are just equal to 1. So it's a special case. All the constants are equal to 1. So in this case, how can we find the variance of the new variable Y, which represents the thickness? So it is the first constant square times the first variance plus the second constant square times the second variance plus the third constant square times the third variance, and each one of the constant is 1. That's why we have 1 square times variance of X1 plus 1 squared times the variance of X2 plus 1 squared times the variance of X3. So simply we have just ones here in the constants, and we are adding variance of X1 plus variance of X2 plus variance of X3. So it's 25 plus 40 plus 30, and the answer is 95 nanometers squared. So just a comment here. We are finished with the question actually. So we blindly applied the formula that we have learned. If Y is a linear combination and if these variables are independent, then the variance is simply a linear combination, C1 squared times first variance and so on, plus C2 squared times the second variance, plus C3 squared times the third variance. And in this specific example, the constants are all ones. Now, what is the idea of error propagation here? We just notice that the variance of the total is the sum of the other variances, which becomes bigger than the individual variances. You know, the variance, you can think of it as the error. So if X1 is the thickness, and we wanted it to have a value, but actually it ends up having some differences, some variations, which the variance captures. You know that the variance captures how far is the variable, how far are the variable values from the mean. So we can always think of it as the error. How far are the variable values from the mean? Okay, so you can think of variance of X1 as the error in the first thickness, variance of X2 as the error in the second thickness, variance of X3 as the error in the third thickness. And we have noticed that the error in the total thickness is just the sum of them, which becomes bigger. So we say the error has propagated. So the error in 1 and the error in 2 and the error in 3 added up to give us the error in the total. So this is the idea of error propagation. That's why we say here this example is about the idea of error propagation. But in any case, we solved the problem without having this in mind at all. So we just apply the formula for the linear combination. Now we can come to case number 2. So in case number 2, we have the following. So still something similar. We have random variables x1, x2, x3 until xp. So it's exactly the same, But in addition to this, we say they are independent. So these are independent random variables. And in addition to this, we also notice that the expected and variance of each is exactly the same. So the expected value of x1 is mu, and the variance of x1 is sigma square. The expected of x2 is also mu, and the variance of x2 is sigma square, and so on. The expected value of xp is mu, and the variance of xp is sigma square. So each one of the random variables has the same expectation, mu, mu, and so on, and the same variance, sigma square, sigma square. Okay, now we need to define a new variable, but just before that, let's just emphasize that the expected of each one of the variables, expected of xi, any one of them, expected of xi is mu, and the variance of xi is sigma square, so that you compare against the previous notation, because in the previous notation, we used expected of x1, and we used the variance of x1. So in short, we just call them mu and sigma square here. Okay, so the new variable, instead of calling it y, let's call it x bar. So let's think of this now as just a new variable, x bar. How do we define the new variable x bar? Also a linear combination, but a special one. We say x bar is equal to the sum x1 plus x2 plus x3 plus and so on until plus xp divided by p. So we divide by how many we have. So our new variable x bar is simply the sum of the variables divided by how many we have, which can be thought of as the average of the random variables. Okay, so this is the case. So this is the case here. The difference between case 2 and case 1 is that our new variable x bar is a weighted sum, but it's a special weighted sum. It is simply the average, so adding up the variables and dividing by p. In addition to this, we assume that each variable, x1 and x2 until xp, have exactly the same expectation, mu, and the same variance, sigma square. And the question is exactly the same. For the new variable x bar, what is the expected value and what is the variance? So let's apply our result from case 1. But to make this easier, let's multiply through. Let's apply this 1 over p and multiply by each term so that we come up with an equivalent form which falls in the way that we are used to, which falls in the structure that we're used to. So x bar is equal to 1 over p times x1 plus 1 over p times x2 plus and so on until plus 1 over p times xp. So what you see here is exactly the same as case 1, but we notice that each one of the constants, c1 and c2 until cp, are all the same, and each one of them is equal to 1 over p. Okay, so for that expression, for this expression, which is simply a weighted sum, what's the expectation? So what's the expected of x bar? We just apply the previous result. The expected of x bar is simply the first constant, 1 over p, times the expected of x1, plus 1 over p times the expected of x2, and so on, plus 1 over p times the expected of xp. So this is what we have. Now let's substitute. We said from the beginning that the expected of x1, let's call it mu, and the expectation of x2, it's also mu because they're all the same until the expectation of xp is also mu. So do you see the terms? 1 over p mu plus 1 over p mu plus and so on until 1 over p mu. So if we take 1 over p as common, so we have 1 over p outside, and then we open two brackets. Inside we have mu plus mu and so on. How many mu's are we adding? How many terms are we adding here? Obviously, we're adding p terms because the original expression has p terms. So let's rewrite again. 1 over p as it is times p mu. So p will cancel with p, and the answer is just mu. So this is the result we would like to emphasize. So if we have random variables x1, x2 until xp, each one of them has an expectation mu. So all expectations are the same. And each one of them has variance sigma square. So all variances are the same. If we define a new variable to be the linear combination, which is simply the average of the random variables, the sum of them divided by p, and we call the result x bar. This is our new variable. We have seen that the expected value of x bar is also equal to mu. Now, what about the variance? The variance can be calculated again using the previous technique. So using the result from case 1. What was the variance of y in case 1? Let's have a peek on the previous slide. How did we get the variance of y? C1 square variance of x1 and so on. So plus C2 square variance of x2 and so on. So let's do the same thing, bearing in mind that each constant, we are here, that each constant is 1 over p. So let's get the variance of the new variable x bar. 1 over p squared times the first variance plus 1 over p squared times the second variance, and so on. And each one of the variances is simply sigma squared. So 1 over p squared sigma squared plus the same, and so on. So we can take 1 over p squared as common. And then inside the brackets, we have sigma square plus until plus sigma square. Again, just as in the previous case, how many terms are we adding here? It's p terms because in the original expression, we have p variables. So we have 1 over p squared times p sigma squared. So this p will cancel with one of these, and we have sigma squared over p. Again, so what is the result here? The result can be summarized here in this slide. So, and we even call it the mean and the variance of an average, of course, an average of random variables. Again, if x1, x2 until xp, each one of them is a random variable, and the expectation of each is mu, and the variance of each is sigma square. So each one of them has the same expectation mu and the same variance sigma square. If we define our new variable to be the average of the random variable, so if the new variable x bar, we call it x bar, is equal to x1 plus x2 plus and so on until plus xp, and then we divide by p. We have seen in the previous slide, we have seen in the previous notes here that the expected value of the new variable x bar is simply mu, and the variance of x bar is simply sigma squared divided by p. I hope it's clear, and we can come to case number 3, or the last case here in our linear combinations. So this case is very similar to case 1. It's very similar, but we just add something. We just add something small. So what do we say here? x1, x2 until xp are random variables, but they're not just random variables, they are normal random variables. So each one of them has a normal distribution. This is the addition. This is one of the additions here. x1, x2 until xp are random variables that have a normal distribution. So each one of them has a normal distribution, and they are also independent. So this is the special case that we have. Okay, and the expected value of each one of the variables is called mu I. So the expected of x1 is called mu1. The expected of x2 is called mu2, and so on. The same for the variances. The variance of x1 is called sigma 1 squared. The variance of x2 is called sigma 2 squared, and so on. What is our new variable? Our new variable y is c1x1 plus c2x2 plus and so on until plus cpxp. So it's exactly the same linear combination as in case 1. Exactly the same linear combination. But the only thing that we know in addition to case 1 is that each one of these variables also has a normal distribution. So this is something that we did not say in case 1. Actually, in case 1, we did not care about the distribution. We just said that x1 through xp are random variables. That's it. And for each one, we know the expectation and we know the variance, and we just expressed the expectation and the variance of the new variable y. So let's do the same thing and then come back to the normal distribution. So if y is defined as the linear combination, so how can we express the expected of y? It's equal to c1 times the expected of x1 plus c2 times the expected of x2 plus and so on until plus cp times the expected of xp. But we know that these expectations are called mu1 and mu2 and so on. So in short, the expected of y is c1 mu1 plus c2 mu2 plus c3 mu3 and so on until plus cp mu p. So what you see here is exactly the same as case 1. What about the variance? Because they are independent, so we don't have the covariance terms, and the variance of y is simply c1 square times the first variance plus c2 squared times the second variance plus and so on plus cp squared times the last variance. So in other words, the variance of y is c1 squared times sigma 1 squared plus c2 squared times sigma 2 squared plus until cp squared times sigma p squared. So this is the variance of y. Actually, getting this expected value, this expression for the expected of y and the expression for the variance of y, we don't need that the variables to be normal. So this is true even if the variables are not normal. But what else can we say if we know the variables are normal? And this is what we add here. In short, if x1 and x2 are normal, then y is also normal. So bear with me and notice that we say that y as defined to be the linear combination c1x1 plus c2x2 and so on plus cp(xp). First of all, the distribution of y is also normal with this expected value and this variance. This is our case 3. I think it will become even better with the example. So this is our example, and again, the best way to talk about it is using my own notes. That's what we have. So this is our example of slide 67. We have a rectangular manufactured part. This manufactured part has the first dimension, we call it x1. The second dimension is called x2, so the length and the width are x1 and x2. And the question here, in the question itself, it is given to us that x1 is a normal distribution. This is a normal random variable with mean 2 and with standard deviation 0.1. So you see here, x1 is a normal distribution with an expectation of 2 and the standard deviation equals to 0.1. And it's also given to us that x2 is also a normal variable with expectation 5 and standard deviation 0.2. So again, x1 normal variable with mean equal to, so this is mu x1 and this is sigma x1, 0.1. x2 is a normal variable, this is mu x2 and this is sigma x2. So mu x2, the mean of x2 is equal to 5 and the standard deviation of x2 is equal to 0.2. In addition to this, the question says that x1 and x2 are independent. Let's have a peek here. Also assume that x1 and x2 are independent. Now, what is the question? The question is not about x1 and x2 themselves. The question is find the probability that the perimeter exceeds 14.5. Here, determine the probability that the perimeter exceeds 14.5 centimeters. Everything is in centimeters in this question. So we would like to find this probability that the perimeter is greater than 14.5. Obviously, what is the perimeter in terms of x1 and x2? From simple geometry, the perimeter is 2x1 plus 2x2. So what we want to calculate is the probability that 2x1 plus 2x2 is greater than 14.5. To make things simple, let's just define y to be our new variable, which is equal to 2x1 plus 2x2. Where did this come from? Because we said perimeter of a rectangular shape. So we have y 2x2 plus 2x1. Now, how can we get the probability that y is greater than 14.5? We cannot get this probability unless we know the distribution of y. And luckily, we have our third case, which tells us y has a normal distribution. Why? Because x1 and x2 are normal, that's given. In addition to the fact that y is a linear combination of the x1 and x2, so this tells us that y is also normal. So we have applied this fact. If y is a linear combination of normal variables, then y itself has also a normal distribution. So we know that y is normal. Is this enough? No, it's not enough. So that we can use our tables, our normal tables to get this, we have to know the expected of y and we need to know the variance of y. So how do we get the expected value of y? Using the linear combinations, using this formula, the expected value of y is equal to 2, which is a constant, times the expected of x1 plus 2, the constant, times the expected of x2. So 2ex1 plus 2e of x2, substituting 2 times 2 plus 2 times 5, which is equal to 14. So we just use these numbers. This is the expected of x1, and this is the expected of x2, and we use the constants, and we applied the formula. The answer is 14. Now, what about the variance? Since x1 and x2 are independent, the variance is given as the variance of y, c1 squared variance of x1 plus c2 squared variance of x2. Okay, so let's just substitute. 2 squares 4, 2 squares also 4. So we have 4 times the first variance plus 4 times the second variance. But we have to keep in mind that what was given in the question was the standard deviation. Let's have a peek here. the standard deviation is 0.1 and the standard deviation is 0.2. But what we need in the formula is the variance. So variance of x1 and variance of x2. So we need to square the 0.1 and the 0.2, and this becomes our correct formula. So 4 times 0.1 squared times 4 times 0.2 squared, and the answer is 0.2. You can verify. Let's put things together. So what do we know? What did we notice? We noticed that y is normal. Y, which is the perimeter, has a normal distribution with mean 14. So mu y is 14. Here we just obtained 14. And sigma y is the square root of 0.2. Why the square root? Because what we had here is the variance. And if we need the standard deviation to use in the formulas, we have to use the square root of what we have obtained here. Now, what was the question? Let's go back to the question because we're almost done. So we need to find the probability that y is greater than 14.5. Now, we are back in chapter 4. Y is a normal distribution with mean 14 and standard deviation root 0.2, and we need to get a probability. So what do we need to do? We need to standardize. So we move from y to z, which is the standard normal. So we say that this probability is equal to the probability that z is greater than, and then we standardize. We take the 14.5, we subtract the mean, and we divide by the standard deviation. But we have to be careful. We subtract the mean for y, and we divide by the standard deviation for y, root of 0.2, which depends on the values that we have calculated in the previous slide. Now, if we use the calculator, this has a value of 1.12. So at the end of the day, we need the probability that z is greater than 1.12. Now, how do we do that? We use our tables, our normal distribution tables from chapter 4. But since this is greater than, so we have to do 1 minus the value because the table is giving us the probability to be less than a value. So if we go to the table and check 1.12, you will find that the probability that corresponds to this is 0.870762, but we have to subtract it from 1. So 1 minus this value is 0.129238, as in the actual slide. It says 0.13, but we just obtained the value more accurately. And this finishes our lecture. Thank you so much, and see you next time, inshallah.